We're now going to use what we know about dot products to look at something called vector projections. There are certain times when we only care about how much a vector points in a particular direction. For example, if we have a force that's acting in one direction and we want to move an object in a different direction, we need to be able to figure out how much of the force is going to be acting in the direction of the movement we desire. Projections measure this directional influence. And we'll see as we proceed that dot products are what make projections precise and computable. Let's take a look at what we mean by a projection before we break it down into how we compute a projection. Let's imagine we have a vector v, which has components v1 and v2, and a vector w that has components w1 and w2. So I'm going to draw v here, and then I'm going to draw some other vector w. And we can see that between them there is some angle, theta. To get the projection of v onto w, which we write as projection of v with a little lowercase w, so this is projection of v onto w. What we're going to do is drop a line from the end of v down to w so that it's perpendicular. This creates a new vector along w. Let me use a better color for that so it's more obvious. This vector right here, that vector is our projection vector. That is the vector that we're going to note as the projection onto w of the vector v. In order to come up with the components of this vector, we're going to look at two values. We're going to first look at the scalar projection, and then we'll look at the vector projection itself. The scalar projection of v onto w is going to give us the signed length of the projection of v onto w. So in other words, it's the magnitude of that vector that we get, but it also tells us whether or not we're going in the same direction. So let's see where this formula comes from. If we look at our earlier picture, we have this image here. We can see in our triangle that we have a right triangle, and so the purple side of the triangle, the length of that side is the magnitude of v. The other side, the pink side, the length of that is going to be the absolute value of the scalar projection of w onto v. In other words, this is the magnitude of the projection of v onto w. We can use trigonometry then to note that the cosine of theta is going to be equal to this scalar projection of w onto v divided by the magnitude of v. But we know from dot products that the cosine of theta is also equal to v dot w divided by the magnitude of v times the magnitude of w. So if we rearrange this, we get that the cosine of theta times the magnitude of v is equal to the scalar projection of v onto w. Replacing cosine theta by what it's equivalent to, we get that v dot w, the dot product of v and w, divided by the magnitude of v times the magnitude of w, all times the magnitude of v, gives us the scalar of v onto w. We can obviously cancel out the two magnitudes of v that fall in that formula, and so we end up seeing that the scalar of v onto w is going to be v dot w divided by the magnitude of w. Since this scalar projection gives us the length and direction of the projection vector itself, we can use that then to come up with this formula for the projection. We'll look again at our picture. And we can see that the projection of V onto W is going to be some multiple of a unit vector in the direction of W. So in order to find it, we need to do two steps. The first thing we're going to do is we're going to find the unit vector in the direction of W. Then, to get the correct length for our projection vector, we're going to multiply by our scalar projection. That also gives us the correct direction, because you can imagine a scenario where V and W are not pointing in the same direction. Here's W going this way. Let me make it green to match the original picture. W goes this way. Then we have to imagine here's a negative W over here. And our projection vector would go in the opposite direction, which is why we need our scalar to have both length and direction built into it. So using these two steps, first of all, from step 1, we know that we're going to call this W hat. We know that W hat is equal to W divided by the magnitude of W. We also know that the scalar, this quantity here, is equal to V dot W divided by the magnitude of W. So if we put those together, we're going to do V dot W. So our projection vector then is V dot W over the magnitude of W, that's its length and direction, times the unit vector, which is V dot W divided by the magnitude of W. I should be careful here. I'm going to put an X for times because we have the dot product in there as well, times W over the magnitude of W, which tells us we're doing V dot W, the dot product, divided by the magnitude squared times the vector W. And that will give us our projection vector. So taking one more look at those formulas, we see that the scalar projection gives us the signed length of our projection vector. The vector projection gives us the actual projected vector. We can compute its components. And we can see from the formulas that both of them depend on our dot product. Okay, for our first example, we're going to find the projection of the vector V equals 4, 2 onto the vector W equals 1, 3. And so we know that this projection vector, projection of V onto W, is going to equal V dot W over the magnitude of W squared times the vector W. Let's compute the dot product first. V dot W, we can do that component-wise. We're going to do 4 times 1 plus 2 times 3, and we get to 10. Now we'll do the magnitude of W. That is going to be the square root of 1 squared plus 3 squared, which is the square root of 10. But of course, we're going to square that, and we get 10. So now when we plug that into our formula, V dot W is 10. The magnitude of W squared is 10. W is the vector 1, 3. And so we see that the projection of V onto W is actually the vector W itself. All right, in this example, we're going to look at the scalar and vector projections in 3 dimensions. So we'll start off with the scalar projection. We're looking at the scalar projection of the vector 6, negative 2, 1, that's V, onto W. And we know that that is V dot W divided by the magnitude of W. So V dot W, we can do that component-wise. We're going to do 6 times 2 plus negative 2 times 1 plus 1 times 2, 1 times negative 2, excuse me. And so we get 12 minus 4, which is 8. The magnitude of W is going to be the square root of 2 squared plus 1 squared plus negative 2 squared, which is the square root of 9, which is 3. So we see that our scalar projection of W onto V is equal to 8/3. So that tells us that our vector has a length of 8/3 and it is pointing in the same direction as U or V. There's no U in this. It's pointing in the same direction as W. Okay. Now let's look at the projection. So this time we're computing a vector rather than a length. And we know the formula for that is, well, we can take the scalar, 8/3, and we can multiply it by the unit vector W hat. That's the unit vector in the direction of W. Which is 8/3 times the vector W divided by the magnitude of W. So we get 8/3 times W divided by 3. So we're going to take 8/9 times each of the components of W to get the vector 16/9, 8/9, negative 16/9. In our final example, let's look at force. So we have a force that is given by the vector 10, 4. And we have an object that's moving along the vector 1, 2. And so what we want to know is the component of the force in the direction of that vector. In other words, we want to know what is the magnitude of the force that's going in the same direction as our vector. So this is a question about, this is the same as asking, what is the scalar projection of that force onto, I'm going to call this vector M, onto our motion vector. And we know, of course, that that's, or let's call it D for direction, because that's a little more standard. So we'll call this direction D for direction. We're going to look at the projection, the scalar component of the projection of F onto D. So we know that that is going to be F dot D divided by the magnitude of D. So let's compute those separately. F dot D is going to be 10 times 1 plus 4 times 2, which is 18. The magnitude of D is going to be the square root of 1 squared plus 2 squared, which is the square root of 5. So we see that our scalar component is 18 divided by the square root of 5, which is 9-ish, a little less than 9 perhaps. But if you look at the actual magnitude of F, the magnitude of F is the square root of 10 squared plus 4 squared, which is the square root of 116, which is bigger than 10. So we can see that because the force is not pulling in the exact same direction as the vector, the motion, some of the force has been reduced, and we have only 18 divided by the square root of 5 units of force. All right, wrapping up as usual with a quick summary. We can see that projections are going to allow us to measure the directional influence. We have two kinds. We have a scalar projection, that's just a number. And then we have a vector projection, which is a vector itself, and they're going to serve different purposes. For both of them, when we compute them, we need to use dot products. We also use magnitudes. We saw that in both formulas as well. And we're going to see shortly that projections are essential for computing work and doing force analysis.